In this lecture, we're going to introduce the idea of matroids and also use matroids in combinatorial optimization problems. Unlike submodular functions, which are functions, a matroid is instead an algebraic structure. An algebraic structure is defined as sets that have properties. In this case, we're going to look at two different sets, U, which is a ground set of elements, and I. I is a set of subsets of our ground elements. We call I the set of independent subsets of U. The key to this algebraic structure is I and the properties that I has. In particular, I has three properties, and these three properties make it a matroid. The first property is that the empty set is an element of I. That is, the empty set is an independent set. Second, if we have two sets, A and B, and A is a subset of B, then if B is an independent set, then A is also an independent set. We can think of this as an inheritance property. If there's a set B that's independent, then every subset of B is also independent. That is, subsets of B inherit the independence property. The third property is the augmentation property. If we have two sets, A and B, that are both independent, and A is somehow larger than B, then we know that we can find some element in A so that we can augment B by this element, and this augmented set will remain independent. So again, we have some set A that's larger than B, and we can take B and augment it by at least one element in A, and this will remain independent. These are the key properties of a matroid. We're going to show some examples of matroids, and particularly we're going to show the inspiration for matroids. The inspiration for matroids comes from linear algebra, and specifically a matroid is a model of a set of independent vectors. We're going to look at independent vectors in terms of the matroid terminology. Our ground set is going to be a set of vectors, v1 through vn. And intuitively, I is going to be the set of all independent vectors of our ground set, v1 through vn. To make sure that this is a matroid, we have to make sure that it satisfies all the properties of a matroid. So we have to check that I satisfies properties of 1 through 3. The first property says that the empty set has to be independent, and this is the case. The empty set of vectors is an independent set of vectors. Second, we have to check the inheritance property. If we have some set of vectors, then we can remove a vector, and this set of vectors will remain independent. This is a general property of linear algebra. So we satisfy property number 2 as well. To see property number 3, we look at two sets of independent vectors, say A and B, and we have that the set of independent vectors A is larger than the set of independent vectors B. If this is the case, then we know that we can find a vector in A to add to B, and this will remain a set of independent vectors. That is, we can find an element of A, augment B by this element, and this augmented set will remain independent. This again follows from the properties of linear algebra. So we've satisfied property 3 of the matroid. So our inspiration, our idea that independent vectors form a matroid, turns out to be true. Matroids, or independent vectors, satisfy the properties of a matroid. The interesting thing about matroids is that we can expand the sense of independence in the matroid sense well beyond what it means in the linear algebra sense. In particular, we can expand it to a lot of different graph structures. In this example, we're going to go through what a forest is and show that this collection of forests in a graph form an independent set. Before we do that, we have to introduce a few different ideas. First, we'll introduce trees. Trees are pretty straightforward. There are any acyclic subgraph that's connected. So, for example, the edges in fuchsia form a tree. They're acyclic and connected. The edges in blue also form a tree. They're acyclic and connected. However, the edges in green don't form a tree since they form a cycle. A spanning tree is any tree that touches every node in the graph. In this case, the edges in fuchsia do form a spanning tree since every node touches at least one edge in the graph, or of the fuchsia edges. However, the blue edges do not form a spanning tree because there's at least one node, in particular this node, that doesn't touch any of the edges inside of the blue edges. A forest, the object of interest, is any collection of trees. that is, any collection of acyclic connected subgraphs. These don't necessarily need to be spanning trees, but also a spanning tree does form a forest. In fact, any tree forms a forest. It would be a forest with exactly one tree. The set of all forests in a graph form a matroid. In this case, the ground elements of our matroid, the set U, is going to be the set of all edges of the graph. The independent sets are going to be the sets of all edges that form a forest. To make sure that this is a matroid, we need to make sure that the set of independent sets satisfies all the properties of a matroid, and it satisfies properties 1, 2, and 3. To show that it satisfies property 1 is straightforward. The empty set of edges, that has no edges, forms a forest. This is an acyclic connected subgraph. To show that it satisfies property number 2, the inheritance property is also rather straightforward. If we have two sets, A and B is an independent set, then A has to be an independent set. In this case, that means that if B is a forest, and we remove some of the edges of B, then the resulting object also has to be a forest. This is true because by removing edges, we don't introduce any new cycles, and so the resulting structure has to be a forest. The final property, the augmentation property, requires a little bit of work, and that's why it's starred. Recall that the augmentation property says that if we have two sets, A and B, and A has more elements than B, then we have to find some element in our ground set that's also in A, so that we can augment B by this element, and B retains its independent property. In this case, this means that we have two forests, the forest A and the forest B, and the forest A has more edges. We'll have to be able to find some edge in A, so that we can add this edge to B, and B will remain an independent set. That is, B will remain a forest. The proof of this fact is relatively straightforward. First, we make an observation. If we have some forest F that doesn't touch some node V, then we can add all of the edges that form a path from F to V, and F remains a forest. We can use this fact now. If we have two forests, A and B, and A has more edges than B, then there's at least one node in A that's not touched by B. We can then add the path from B to this node and retain the forest property. To see how this works, we have a small example of two forests. In this case, both forests are trees. The forest A has more edges than the forest B, so we can find some edge to add to B, and it will retain the forest property. In this case, we're going to look for a vertex that B doesn't touch. In this case, we'll circle this one in green. We can then add the path from the forest B to this vertex, and B remains a forest. The reason we're so interested in matroids is because the matroid optimization problem is one that arises frequently. In the matroid optimization problem, we're given as input the ground set of elements and also the set of independent sets. In addition, every element in our ground set has some weight associated with it. The objective in matroid optimization is to find some independent set of maximum weight, where the weight of a set is the sum of all the weights inside of that set. When we apply this to particular matroids, we end up with interesting combinatorial problems. For example, when we apply it to the matroid consisting of forest, we get the maximum weight spanning forest problem. In this case, the maximum weight spanning forest has to be a tree, so this is equivalent to the maximum weight spanning tree problem. In this problem, we're input a graph G equal to VE and a weight for every edge. The objective is to find a tree of maximum weight, or equivalently, in this case, a forest. In addition to introducing some interesting combinatorial problems, the matroid optimization problem can be solved very efficiently with a greedy algorithm. The greedy algorithm works as follows. We're going to iteratively build an independent set. We'll start with the empty set. The empty set, always being an independent set, will be independent. Then we look through all the elements on our ground set, and we identify whether we can add at least one element to our set S and retain independence. If this is true, then we find the element that we can add to S that has the maximum weight. And recall that by adding this element EM, we're going to retain the independence property. Then we actually add this element to our independent set S, and then we iterate. We come back, and we find, again, if we can add another element to the set S and retain independence. If at any point we can no longer add an element to our set S, that is, adding any element will break the independence property, then we stop the algorithm and we output whatever set we've constructed. It turns out that this greedy algorithm finds the optimal solution. It would be great to conclude that we could find, for any Matroid problem, some efficient algorithm, but there's a little bit of a problem with this algorithm. In both of these steps, both identifying if there is an element we can add and retain independence, and also finding the maximum weight element, are problem specific. So to analyze the runtime of this algorithm, and specifically to analyze whether it's efficient, we have to verify that both of these steps can be actually solved in the problem at hand. Because of the usefulness of Matroids and this greedy algorithm in particular, we study Matroids quite frequently. And a common strategy for solving problems is identifying that there's some Matroid structure in the problem we're looking at. If that's the case, then we can develop the greedy algorithm by filling in these two problem-specific pieces of information and executing this greedy algorithm. Usually this is going to result in an efficient algorithm that solves the problem very quickly.